Hi there, and welcome to another Haltech What's So Special About. And today, we've got the mighty Honda K24 here. Okay, so let's start with a little bit of history about Honda itself. Believe it or not, Honda's founder, Soichiro Honda, actually started out making piston rings for Toyota. He then moved to motorcycles in the late 1940s, which were actually assembled in a wooden shack. The bikes were followed by small pickup trucks in the early 1960s, and then the first ever Honda production car was the S500 Sports Coupe. That was in 1963. Why a sports car? Well, it turns out that old Honda-san was mad about motorsport. In 1954, he decided Honda motorcycles would race at the Isle of Man TT. It took him 5 years to develop the motorcycles, and on debut in 1956, Honda won the Manufacturers' Team Award. In 1961, with motorcycle legend Mike Hallwood on board, they won 2 of the TT races. Not only that, they also won the 250cc and the 125cc titles in the World Motorcycle Grand Prix season. With that success under their belt, in 1962, Honda decided to aim for Formula One. A few more years of development, and Honda was on the podium, with a win at the 1956 Mexican Grand Prix. Honda's been racing in Formula One and supplying engines on and off throughout the years, right through to the present day. The highlight of which is probably Honda's partnership with McLaren in the late 1980s and early 1990s, and the relationship with the late, great Ayrton Senna, who was instrumental in the development of the original Honda NSX, possibly one of my favourite sports cars of all times. It's such a unique and beautiful car. Now, we could talk for days about Honda's involvement in the Japanese Super GT series, the British Touring Car Championship, the World Touring Car Championship, IndyCar or Le Mans, and more motorcycle racing than you can poke a Kickstarter at. But what it all boils down to is that Honda has done a huge amount of motorsport, and that motorsport experience has led to Honda's power plants not only being very efficient, but also incredibly well engineered and extremely reliable. Which brings us to this power plant, the Honda K-Series. For years, the K-Series has been the favourite swap of front-wheel drive Hondas. Fans of golden era 90s Hondas have been binning their D, F, even B series engines in favour of the K series since they hit the scene in the early 2000s. There are now entire companies devoted to manufacturing parts for K swaps into these older Hondas and a whole bunch of other model cars. The Honda K series was first offered in 2001 in the hot hatch Type R trims of the Civic and Integra, and is still today offered in DI form of several Honda and Acura models. Nearly a 20-year lifespan means that there's plenty of variants of this engine to choose from, and it's now done 20 years of engine development from the early 2000s right up to today. The most popular models for swaps and performance applications are the early K20 engines from the 2001-ish to 2006 EP3 Civic and DC5 Integra, and the K24 engines from the 2002-ish to 2008-ish Honda Accord and Acura TSX. These are my personal favourite. Often pushed as the best performing package is a hybrid combination of both, with the high-flowing K20 head and the larger displacement K24 bottom end. In recent years, rear-wheel drive K-swap markets absolutely exploded, with several aftermarket manufacturers producing rear-wheel drive gearbox adapters, conversion parts, and even full kits to swap the K-Series into Honda S2000, Mazda MX-5, Mazda RX-7, and even the Nissan S and some R chassis. With pieces and parts from these manufacturers and a little fabrication knowledge, it is possible to put Honda's incredible 4-cylinder into virtually any chassis that you prefer. Within this segment, the K24 from the 2009 to 2014 Accord TSX is also extremely popular due to its massive supply, its low cost, and advantageous exhaust packaging, with the exhaust manifold runners being cast right into the cylinder head. The Honda K-Series engine has enjoyed continued success in motorsports, from drag racing to time attack, wheel-to-wheel circuit racing, and even European autocross. When used in drag racing, the K-Series does have a torque advantage over the older Honda designs, and the rules are actually set up in a way that allow advantages to the older B and H-Series engines to even the playing field a little bit. The fastest all-motor K-Series races are all in the 8s now in the quarter mile, and the turbo cars are pushing deep into the 7s. These cars are getting so fast that racers are now employing all-wheel drive conversions to try and go even faster. Time attack racers like James Horton and Rob Newen rely on high horsepower K-Series to set records on tracks all across the world. A detuned K-Series is the winning formula in power-to-weight racing series like Gridlive's Touring Cup, where over half of the top contenders are K-Series powered. In European autocross, legendary racers like Marcus Thomas use a 2.7 litre stroked version of the K-Series, and this thing propels his buggy to numerous wins and championships. With few common flaws, a standard compression check is just about all that's really needed to ensure a healthy engine's chosen for your project. If you've got the time or resources to inspect an engine before purchase, it's worth pulling off the valve cover and having a quick look at the valve train and camshafts. You can tell if the thing's been really looked after or not. What you're looking for here is like an oil sludge buildup or heavy oil varnishing. This could be evidence of a lack of routine maintenance and may result in premature camshaft or bearing wear. And let's be honest, most of these things are in family commuters that have done a couple of 100,000 miles or kilometers and are probably getting serviced. They're supposed to be every 10,000, 15,000 kilometers, and then people are pushing them out to 20, 25,000 kilometers. So just be very wary of that. On to the main event, the K-Series. At first glance, Honda's K-Series doesn't appear to be worth any high performance merit. Just another pedestrian 4-cylinder mill known for excellent fuel economy. From the factory, it's a bit boring. It doesn't have a turbo, and it's got a pretty modest rev limiter. What's not immediately evident is the platform's potential. It's a robust all-aluminium double overhead cam engine outfitted with a coil-on plug ignition system, roller rockers, a forged crankshaft, cast iron sleeves, and Honda's elegant VTEC, which includes electronic lift control and variable timing control. Simple and ingenious in design, Honda's electronic lift control allows one single camshaft to have essentially two profiles. The low profile provides excellent fuel economy in cruising situations, and a more aggressive high cam profile allows greater airflow and top-end performance. The sound of the crossover from low to high cam is something Honda's absolutely famous for. You get that honk when it comes onto the second camshaft. New for the Honda 4-cylinder in 2001, the K-Series had variable timing control via ECU-controlled hydraulically adjustable cam gears. This complement of technologies that allowed both economy and performance was dubbed iVTEC as the next generation of Honda's revered VTEC system. K-Series tuners have expanded the horsepower out of these engines by outfitting turbochargers, superchargers, and even nitrous. Completely stock long blocks, which is what this thing is, holds upwards of nearly 400 horsepower at the wheels. Swap out pistons and rods, and the stock crank and sleeves can handle 700 horsepower. Fully built engines can achieve impressive horsepower numbers cresting over the 4-digit mark. Well, we've spoken about this thing enough. It's time to get down and dirty. Let's strip it down and see what's inside. Just a note, I have spent the day already disassembling this thing, cleaning so much oil out of it so I don't destroy the studio here. It's been reassembled, so just keep that in mind that I've done that so that we can get through the video nice and quick and don't bore you to death. All right, well, all we're going to do is we're going to start at the top. We're going to work our way down. So we'll pull the rocker cover off. We'll have a look at the valve gear inside. Then we'll just start going through and we'll get right down to the bottom. And today we might even try and pull some pistons out. Well, that's where all the efficiency is. Cylinder head, these camshafts, and what's so special about them is they've got one lobe per valve. It's got 16 valves because it's got 8 valves for the intake and it's got 8 valves for the exhaust side. Twin camshaft, the camshafts are driven by a timing chain. This thing has continuously variable intake cam control. And then we've got our VTEC lift solenoid on the side here. What's absolutely amazing about this thing, like I was saying before, is how essentially it does have 2 different cam profiles. When this solenoid on the side here allows oil pressure through, there's a whole bunch of little locking pins that we're going to get to here that allow basically a different cam profile to be activated, and you get that VTEC honk. In aspirated form, the thing on the low camshaft will say, let's say about 110 kilowatts at the wheels, somewhere around there. As soon as we engage that high camshaft, the thing will make about 145 kilowatts at the wheels. So to put that in perspective, that's a huge power gain on an aspirated engine. This is pretty special, and this is a part of the Honda that I just think is absolutely incredible. So full roller rocker setup as a factory car that makes, like I said, 130 kilowatts, 140 kilowatts at the wheels, that is going to go in all types of family sedans. The engineers absolutely outdid themselves. These engines, amazing. The things that were really nice about it are the caps for the camshaft. The same single cap holds the inlet and exhaust camshaft together. So there's less components in total to hold the camshafts in, less bolts, but it holds the whole thing much more solid because it's one part that's bracing the top of the engine. Really, really nice. All right, so what we were talking about here with the 2 different cam profiles is that we've got the little driving around town cam profile here, and then we've got the big high RPM, high power cam profile here. The magic inside the Honda engine is how we use oil pressure and an electronic solenoid to be able to switch back and forward between cam profiles on the fly. So let me give this a go, trying to explain how this part works. So we actually don't have oil pressure in the engine, obviously. That's going to be a problem for me explaining how this piston shoots out, but I'll do my best to explain it. So I'm just going to pick one cylinder here to explain it on a single cylinder. So this is cylinder 1, cylinder 2, cylinder 3, cylinder 4, intake side. Intake and exhaust work in exactly the same way. What normally happens here is our camshaft is pushing on our rollers here. And normally, I'm just going to leave those 2. This is what's going on. The camshaft is pushing up and down on our rollers, which are in turn pushing up and down on our 2 intake valves. You can see there that I can move them independent of this middle one, which not many cars have. This one's actually doing nothing when we're cruising around town. All it's doing is just chilling out. It's going up and down on the large cam profile, but it's not actuating any valves. Now watch this. I'm going to pull this little bit apart. So at the moment, you can see that everything's working independently. If I pop this one up, if we can see just on the inside here, there's this little piston that's sitting on the inside here. If we applied oil pressure to the engine and we activate the VTEC solenoid, this little piston is going to spit out in this direction. When it spits out in that direction, I'm just going to pull this piston out and see that on this rocker arm, we've got a little piston that's spring actuated here. Can you see that? So what would happen is when we apply a pressure through this piston in turn locks this rocker arm and this rocker arm together. Here, in turn, locking into this arm. So I'll manually do that now. That goes into there, that goes into there, that goes into there. And what we end up with is, here we go, we'll move that one. You can see now, these 2 are locked together. If we had oil pressure here pushing this piston out, this third arm would also be locked together. So then these three would be working in unison. I might pop that out, and this might be a better way to show it. These three would now be working together and working off the center or off the high lift part of the camshaft. Now that we're past the magic of the variable valve lift system, remembering that we also have, this is the exhaust side. Let me put the intake side here. We've also got the continuously variable cam control as well. So this is the one that can advance or retard the intake cam. I think a lot of factory cases, about 30 degrees, you can adjust these to get up to 50 degrees of intake camshaft movement. The way that works is we pulse this solenoid here, we let oil in to advance it, we pull oil out to retard it, and we hold it at a certain position in order to lock the cam in place. So if we wanted to, say, advance the inlet cam, for example, we would open the solenoid to, let's say, 60% of its available flow. We would monitor the cam angle until it advances to the right position. Then we would come back to what we call a lock position or a steady state position on that solenoid, where we might apply, say, 50% of its available flow, which will lock that cam in position so it can't advance or retard. If we then want to retard the camshaft, we might want to operate this valve at, say, 40% of its maximum flow. The camshaft will retard, then we'll come back to our 50% lock state and lock it at the next position. We map this cam angle against all RPM, all throttle position, or manifold pressures. So every time that you're driving your car, this continuously variable camshaft is doing exactly that. It is continuously moving around in order to make the most power across the entire rev range. So think about that in the old school style engine where you had your vernier cam gear. So you'd put the thing on the dyno, you had a bunch of Allen keys in the front of the cam gear. You'd give it a run, see what power it made. Then you would talk to your tuner and say, all right, well, it's making a lot of top end power. I can sacrifice some of that top end because I want to get more bottom end. So you would mechanically move the camshaft a few degrees, give it another run, it would lose some top end, but you'd pick up some bottom end. Then you'd talk to the tuner and decide on, okay, where do I drive the car? Which cam angle best suits me and how do I want to lock it up? So that was how we used to do it, and we used to have to make sacrifices. When it's continuously variable, just tune for the most power everywhere. All right, the next task is a pretty straightforward one. We'll just pull the 10 mils off the side here and pull the VTEC solenoid off. So this one on the side here is the one that's responsible for the oil flow to do the cam switching. The one on the front here is responsible for the oil flow to do the variable, continuously variable cam control. I'll zap this one off. I understand that this one does have problems every now and then, where if you don't change the oil enough, this thing has got some filter baskets down the bottom here, which do fill up with junk. So it might be worth just popping that off, having a bit of a look, clean it up, and then slap it back on if you've got any cam control switching problems. This is where the timing chain tensioner is. So this is a hydraulically assisted tensioner. Basically, when you put a chain on, you've got a little sort of hole in here that you put a pin into after you've pulled back that tensioner, set everything up, pull the pin, the timing chain goes tight, and away you go. So nice to have a little inspection plate there. This is the crank sensor itself. So this is a Hall effect crank sensor. So it's got a power supply, a ground supply, and a signal wire that comes out. It measures a tone wheel that's mounted on the actual crankshaft itself. Here we go. That's what the sensor looks like. So it's just got a 3-pin connector. It faces down like this, looking directly at the crankshaft. And when we get the bottom out, we'll be able to see how many teeth are on the crankshaft and the pattern that's there. The crank pulley. If you've seen any of the other videos, these ones always get me. Today, this crank pulley got me as well. One thing to note is that Honda do it a little bit of a different way, where there's a special tool that actually holds the outer of the harmonic dampener here, and then you can use a rattle gun on the inner to try and get the bolt out. We had all sorts of fun with that. So dampener off, a Woodruff key. So the Woodruff key sits in the crankshaft and then locates in the balancer to stop it spinning. The grooves on this are really interesting because it locates onto the crankshaft with the Woodruff key, but it's got a whole bunch of grooves here. There's no receiver grooves on the crankshaft. So these grooves are here simply to make it easy to get this on and off. On other brands of engines, they don't have any sort of notchings or anything like that on the inside of the balancer, making it so that you've got two metal surfaces jammed together makes it almost impossible to get balancers off sometimes. So I really appreciate that, and I think it's a really nice idea. So there we go. So that is the cam solenoid that's controlling the oil to the inlet cam gear. So basically, as this plunger moves forward and backwards, it allows oil through these filters to either fill the cam solenoid, empty the cam solenoid, or hold it a steady state. That's another one that's got a whole bunch of filter baskets across the front of it as well. So if you do get a high K wrecker engine, might be worth pulling that out and giving it a bit of a clean before you start tuning it. Timing chain comes down through to really nice, really long tensioners and guides that hold everything in place and make it so there's no rattles. Very rarely have timing chain problems in these things. Down the bottom here, where we were talking about our crank sensor before. So the crank sensor was coming in through the side here of the timing cover case, and it's looking at this tone wheel here. And that's what it looks like. So when they talk about your crank trigger or your cam trigger on your engine, how many teeth it's got, well, we can count it here. So this thing has got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and a little extra tooth sitting there. And that's what the Honda K24 trigger type is. The sensor sits like this. As the teeth go around, it counts all of the teeth. It's a really nice crank trigger for a factory engine, so beautiful. Keep in mind this engine is going for a rebuild, so most of this stuff is going to get binned, so that's why I'm being sort of pretty rough with most of it. All right, and that's about all we've got time for. No, I'm just kidding. I'm sure that you've got this far. You want to see the bottom of it? You want to see the crankshaft come out? All right, well, first thing we better do is take that cylinder head off. Nice long head bolts. I did notice that it had a set of aftermarket camshafts in it. It has got titanium retainers in the springs as well, so there must be something going on. So the inlet manifold would normally be sitting on here. This particular engine looks like it's had a little bit of porting work done on there so that the air's flowing in a little bit nicer. If we get the camera right in here, we can actually see, which is pretty cool, the tract going in where the air's going in, the little bit in the top where the injector is actually sitting to spray the fuel in, and then the back of the inlet valves right there. So you can see that the way that the air's going into the engine, I understand it's not fully indicative of the whole airflow modeling of the thing, but just looking at it and seeing how close and the shape of everything is really, really nice. So we can see here, 4-cylinder, it's got cast sleeves like we were talking about. It's of an almost open deck style design, so there's plenty of cooling. Let's flip it over. We'll pull the sump off and then start to get to business on the crankshaft end. So inside the sump there, the sump, very basic, no baffling, no anything at all. Just a place to hold the oil. Because this is something that when we pull this, I was shocked to see this. This is cool. This is the oil pump assembly, this whole thing. So it's not something that's tiny that just sits in the front of the timing cover case, and it's not direct driven off the nose of the crankshaft. It's actually got its own little drive chain, its own little set of tensioners. So there's the drive gear for our oil pump chain. This is our actual crank sprocket. So it was one of these are driving the cam gears, the other one is the oil pump. So So you can understand now why the sump doesn't have too much baffling in it. It's almost as if the pump assembly itself has got the baffling internal. It's a really, really nice design. I'll roll this over a little bit so we can have a look inside. I'm going to spin that, so that's as if we're spinning the pump around. It's an amazing thing, a really, really nice system. Admittedly, I probably wouldn't want anything going wrong with it, but in saying that, the engines are so affordable that if something ever did go wrong with something like this, you wouldn't get that too deep into it. You'd be onto another wrecker engine and away you go. What you'll notice here is there's no individual main caps for the crankshaft. This is another thing that I'm just envious of. I think it's a really, really nice system where the main caps, a whole bunch of bolts, and then it basically braces the bottom of the block. So this is one of the conversions, like a lot of the RB guys are now doing these sort of bottom end brace systems. Factory Honda. Come on, look at that. Wow. It's solid and yeah, amazing. Absolutely amazing. So if you were going to be building one of these things, rods and pistons are probably the first thing you'd be looking at. The rods physically certainly don't look massive at all. They do handle a beating, so they've obviously got something down with the design and the shape of them, but rods and pistons, that's probably the first thing that's going to fail when you start to be pushing good power out of this thing. You know what, just before I take the crankshaft out, if you ever get told that you need a rear main and your car's leaking, this is the rear main. So this is an oil seal that's on the back of the engine. It sits around the crankshaft and goes into the actual engine block itself and stops the oil from getting from the inside to the outside. So doing a rear main seal, if your engine's in this condition, it's pretty easy. You just grab one and slap a new one on and job done. If it's getting done in your car, slightly more painful. But anyway, that's what a rear main seal is. Now that we've got the crankshaft out, have a look in the block. There's not too much going on. The castings are absolutely beautiful. So for other engines where you'd spend a whole bunch of time grinding to make everything smooth, to get all your nice oil returns and stuff, not the case. You look inside, it's neat, it's clean. It's got oil squirters on the bottom of the pistons. Just looks functional and just works. As a performance enthusiast, this is kind of what you would expect an engine to look like inside. Coming over to the crankshaft, again, not much you can say. The thing's a beast. They don't have problems. They don't break. They don't break at cylinder number 4, so that you end up with, the crankshaft spinning independent of the flywheel. It's got a great oiling system that's not dependent on the nose of the crankshaft, so it doesn't put a huge amount of load on the front. Even on this thing, you can see very little balancing marks. 10 out of 10, guys. This thing is, I didn't expect to enjoy pulling this engine apart as much as I did. And every time I pulled a new part out of it, I thought, oh, wow, makes sense to do it like that. And I can completely understand why this thing has got the reputation that it has. Absolutely beautiful engine. What's so special about the Mitsubishi 4G63? Manufacturing everything from air conditioners, forklift trucks, hydraulic equipment, power generators, printing machines, ships, aircraft, and even railway systems, Mitsubishi shied away from mainstream motorsport until the mid-1960s. But it was in the 1980s that the Japanese car maker made its mark on our industry with its factory-backed World Rally Championship program and its unmistakable performance platform, the Mitsubishi
4G63. And that is the subject of today's video. The 4G63 is a member of the Mitsubishi Series 4G6 family and was first introduced as a 4-cylinder, 2-litre, petrol-powered, naturally aspirated engine in 1980. But it's the turbo version, the 4G63T, that we'll be looking at today. The 4G63T was first seen in 1988 in the Mitsubishi Galant VR4 and later in the more performance-based Mitsubishi Evo Lancer. In North America, the 4G63 was available in the higher trim levels of the first and second generation Diamond Star Motors cars, or DSMs for short. These were a series of sport compact coupes wearing Mitsubishi, Eagle or Plymouth badging. During the late 1980s, the 4G63 equipped Group A Galant VR4 carried Mitsubishi to its first outright World Rally Championship victory. Mitsubishi then homologated the Group A Lancer Evolution and, in the hands of Finland's world-famous Tommi Mäkinen, won the driver's title 4 years in a row. It was from 1996 to 1999. And won the Manufacturers' Championship in 1998. The Lancer Evo also dominated the Group N FIA Championship for showroom-ready race cars. They won 7 consecutive titles in 4 different drivers from 1995 to 2001. Even in 2002, when Mitsubishi came second to Proton in the Group N rally, it was a 4G63 that powered the Proton to victory. Mitsubishi's mainly been associated with rally and circuit cars, but in the last, say, 15 years, the 4G63 engines played a huge role in Mitsubishi-powered drag racing cars as well. In the United States, names like David Buscher and John Shepard pioneered the development of DSMs and the 4G63 for drag racing purposes. Haltech heroes like Aaron Gregory and Devon Schultz are carrying the proverbial torch for machines that clock off consistent 7 and 8 second quarter mile times at over 200 mile an hour. With each year passing, the new records are set and the mighty 4G63 surprises us with times that, truthfully, I never thought would be possible from a 4-cylinder engine. Unbelievable. The 4G63 engine uses a cast iron block and an aluminium cylinder head. The engine block houses a forged steel crankshaft and connecting rods, while the pistons are a cast aluminium. They use a timing belt, so not a timing chain, to link the crankshaft to the dual overhead cams. Depending on the variant of 4G engine, they've got different cylinder heads. A low-performing 8-valve single overhead cam head, a better performing 16-valve single overhead cam, and the best, a 16-valve dual overhead cam, which is also available in 2 different versions, a big inlet port and a small inlet port. The single cam head actuates the intake and exhaust valves via rocker arms, and the adjustment of the valve clearances is required. The cylinder heads with the dual overhead camshafts have been around since about 1987. These engines also have rocker arms, but with automatic hydraulic valve clearance compensation, so a whole lot less work. Like Honda's B and K series engines, the 4G63's head and block were interchangeable with its longer stroke sibling, the 4G64. Combinations of these 2 engines can yield displacement increases up to 2.4 litres out of the little 4-cylinder. The 4G63 can still be found in production vehicles today. This means an overwhelming 40-year lifespan for the little Mitsubishi platform. To add to that, aftermarket support and development is still going really strong on these things. The high-flowing aluminium cylinder head and stout iron block now form the foundation for high power production, with some examples exceeding 1,000 horsepower and billet block examples capable of up to about 1,700 horsepower, but I'm sure neither of them are going to be the limit for very long. The 4G63 block comes out in 2 variations, a 6-bolt and a 7-bolt. This refers to the number of bolts holding the flywheel to the crankshaft, but is indicative of a few other differences throughout the engine. Most notably, the 7-bolt main bearings have narrower journals and are allegedly not as strong as the 6-bolt engines. Therefore, they've become a little bit less desirable for high horsepower builds. The 7-bolt engines also have a tendency for developing what we call crank walk, which is when the thrust bearing on the crankshaft really deteriorates, causing big problems along the bottom end as it fails. A point of contention among enthusiasts is that the 7-bolt's not automatically more prone to crank walk, and that the 7-bolt's crank walk is little more than internet talk. 6-bolt, 7-bolt, depends on what camp you're in. Regardless, when purchasing any 4G63 secondhand, it's important to check the crankshaft for play in order to identify an engine that may have worn thrust bearing and the beginning of that dreaded crank walk. The 4G63 is originally equipped with some balance shafts that are driven by a secondary rear timing belt. This belt's prone to breaking and causing primary timing belt failure. This results in catastrophic engine failure. Deleting these balance shafts and their timing belt is normally one of the first performance steps that any 4G owner takes. But there is a downside to this. The balance shaft does noticeably reduce engine vibration at idle and cruise speeds, but it's a small sacrifice in a performance engine build. If you have a look down through the front of your timing cover case, if you are unlucky, sometimes you'll see that balance shaft belt all down there, all crumpled up with the engine still running. But now on to the good part, pulling this 4G63 apart. This is an Evo 8MR 2-litre stock engine. It was donated by Jeff, one of the Haltech dispatch guys. So if you've ever got anything from Haltech, Jeff may have packed it for you. We pulled this engine out of his car after it started making some funny noises. So we've already had the sump off to have a bit of a sticky beak, but we haven't had any of the top off yet. So we'll pull it off from the top down, see what's actually going on inside. Being a later model engine, being an Evo 8MR, in those cars, the engine sits pointing one way. If it was an earlier model, say a 1G, 2G, DSM, Evo 123, the engine would actually be turned around and facing the other direction in the car. Something worth noting. All right, we're on to the dirty bit, so let's pull it apart and see what makes this thing so special. So before we strip this thing too far apart, I wanted to show you the crank sensor down here with the trigger disc that is on the crankshaft behind the main crank pulley. So all I'm going to do while the timing belt's still on this thing, I'm just going to turn the engine. I am going to turn it backwards and forwards. I know you're probably not supposed to, but the thing's coming apart anyway, so no problems there. If we can get it close up, what you'll actually see is this tooth here that's going through this optical sensor that's mounted just here. So basically that sensor is sitting like that, a plate comes through, a chopper wheel comes through, interrupts that signal, and that's how we get our trigger event occurring, our RPM sensor. There's wide tooth and a narrow tooth on the crankshaft. So that's our crank reference, remembering 4-stroke engine. It's got a little gear down here, it's got a big gear up here. So remembering that, the crankshaft has to spin twice while the camshaft spin once. And because of that, we need to have a camshaft sensor to tell us which cylinder is coming up to top dead center compression. A crankshaft sensor, regardless of the number of teeth on it, will never be able to tell us that. So we'll pull these out of the back here. It's got 3 10mm off the back. We'll have a look at what's in the cam sensor here. As a side note to this, these engines are fitted with waste spark ignition, so they've got 2 ignition coils. It's got 1 coil that sits over cylinder 1 with a plug lead that dangles off it that goes to cylinder 4. Likewise, it's got another coil that goes into cylinder 2 with a plug lead that sits across to cylinder 3. So there's our cover off the timing gear up the top here. And if we look inside there nice and close, we're going to see that it's actually got a wide tooth and a narrow tooth in there on the cam sensor. A 3-pin digital Hall effect sensor up the top here. Probably one of the problems with the 4G engines or the later 4G engines, these cam sensors are a little bit problematic now. If you put a big high-rise turbocharger manifold up there or you've got a dump pipe going across them, when they get a little bit warm, they do tend to be a little bit problematic. So Evo 7, 8, 9, open the glove box, you'll typically find a few spare sensors in there. So what I've just done now is I've wound the motor over so it's not at top dead center. So on this engine, at top dead center, 2 pistons will be right at the top, 2 will be right at the bottom. What I've done is I've turned the engine over so that all the pistons are about in the middle of the bore because I'm going to pull the timing belt off. If I pull the belt off and all the pistons are at the top, there is a chance that if we rotate it, we might end up doing some valve damage. While the belt's still on the front, we can see obviously it's got the 2 cam gears up the top It's got two idlers along here. It's got a hydraulic tensioner. So what happens there is when we're putting the belt back on, this is that grenade sort of style thing where it's got a pin that's all the way back into that tensioner. It's held in with sort of like a grenade pin. Once you line everything up, put it all together, you pull the pin, that tensions everything, then you know your belt's tensioned. Up the top here, we've got our dual variable camshafts. Like I said before, this is an Evo 8 engine. The Evo 9 engine, still 4G63, had what Mitsubishi call MIVEC, or continuously variable intake cam control. What that means is that on the front here, we would actually have a continuously electronically controlled variable cam gear. It has an oil control solenoid that allows oil in to either advance or retard the camshaft, then puts a certain amount of oil in to lock it in position. We actually map that across all engine RPMs and all engine loads in order to basically make the most engine power across all engine load sites. When we look down here at the camshaft, everything's neat and tidy and pretty compact there in the top of the cylinder head. It's got two camshafts. One camshaft does the inlet valves, the other camshaft does the exhaust valves. Of each camshaft, across each cylinder, it's controlling two valves. So that's 2, 2, 2, 2. Under that, we've got our hydraulic lifter and our rocker arm. That rocker arm pushes straight on the top of the valve here. We've got a retainer and the spring. Now that we've got the camshafts out of this thing, we can see a little bit better about what's actually happening and how we are actuating the valves. So in here, this is something that is special about the 4G. It's got roller rockers. Nice little thing. We very rarely have problems with any of these. Then we've got hydraulic lifters, these things here. So that thing is bottomed out on the bottom of the cylinder head. Then that rocker sits on top of there, like this, as so. Then this is where our valve stem sits, just here. Camshaft pushes it up and down. Spinny bit goes right on the camshaft and there's no wear, so that's a really nice thing. Being hydraulically actuated, you don't have to set any of your tappets or anything like that. One thing about these hydraulic lifters, in the Mitsubishis, they do have a tendency to get a bit noisy, have a lot of ticking on cold start, and once they get really bad, all the time. So not a terrible idea to replace them if you're putting camshafts in the engine. I've loosened all the head bolts. I'm just going to pull it off with the head bolts still in there. But bolts pretty straightforward. If you are building one, put a set of head studs in it because you can put enough boost in this thing, it's going to need them. This has got factory multi-layer head gasket. Just pop that off. Geez, it has seen better days, this engine. And it does stink. I don't care what anyone says about the smell of pulling an engine apart. This one smells funny. In the cylinder head, we can have a look at the exhaust ports. Are massive. If we flip it around, the intake ports are equally as large with a little relief in the top for the fuel injector in the factory inlet manifold. Flip it over. It doesn't appear that there's any damage anywhere there, but pretty straightforward. Just a nice, neat cylinder head. Without too much effort in porting or doing relieving for oversized camshafts, the cylinder head really does lend itself to huge, huge horsepower applications because with just drop-in camshafts, no porting or very minor porting, you can make a huge amount of horsepower with this very basic cylinder head. Now that the cylinder head's off, we can see that it is a closed deck style block. So there's not a big water gallery around every single cylinder, not something like an open deck Subaru, for example. So that makes it nice and strong in the cast iron block. There's not too many holes up the top, so it is fairly solid in the deck, and there is quite a lot of meat in between the cylinders here as well. We'll flip it over, have a look at the bottom end and see what's happened down there. Now there's two reasons for pulling this engine down in the first place. The first one is that Jeff wants to build a 2.3 litre billet crank stroker engine. But the second part of that reason is because this engine did start making, well, what Jeff described as a sort of like a bit of a tapping noise. We pulled the sump off. I know what the tapping noise was. Straight away, we'll pull the pickup apart and I'll try and clean it out. There's bearing material in the pickup, so something's gone horribly wrong. If I cast my eyes down and start looking at the bottom of the con rods here, so at the big end bearings, the first bearing on cylinder 4 looks pretty reasonable, normal sort of colour. We'll get a close-up here of the cylinder 3 rod. It's black. So I can wobble it, so straight away the thing's had a serious malfunction. It's spun a bearing, it's done something wrong, so we'll pull it apart and see what's actually happened there. But this is a really good example of that knocking noise. So when you do have something, what people call a bottom end knock, this is exactly what that noise would have been. It makes the bottom of that rod so hot that before you know it, that bearing will just disintegrate, it'll go through the engine, it'll destroy absolutely everything. So I wouldn't be surprised in this engine if the main bearings as well, so the ones holding the actual crankshaft in, have got bearing material through them and the whole thing's just scored and destroyed. So as we pull it down, we'll suss that out. So this is something we don't really get an opportunity to sort of show you or explain what this noise is really like, but when you free rev the engine up, so that means in neutral, no clutch, or in neutral in automatic transmission, if you free rev the engine up to 2,000-3,000 RPM and you hear a ruck, ruck, that noise is so loud when you're in the car that you know there's something horribly wrong. I can make that noise here, so I'll just get close with the mic. If you can hear that noise, but imagine that at 2,000 or 3,000 RPM, that's a death rattle. So let's pull it apart and see what's in there. So here's our oil pickup. So this is the thing where the oil pump is pulling oil up out of the sump through this connection here, which has got a gasket. If that gasket leaks and we've got a problem here, that means that we would be dropping oil pressure, so it's important to make sure that gasket is in place. Comes up through the oil pump and then down through the oiling system of the engine. So I don't know if we can get a close-up of that, but that's what's actually in the pickup. I'm excited to pull this apart now. It's got this windage tray here, which is a pretty nice thing. So that serves no purpose other than to settle the oil down when you're revving the engine hard to make sure that it doesn't aerate and to make sure that the pickup is picking up solid oil and not sort of a bubbly, foamy sort of thing in the sump. Having a look in there, I couldn't see the front 2 rods before. They look like a nice colour, so it is cylinder 3 is the one that's had a catastrophic failure. Off the top here, we've got our main bolts that are holding the crankshaft in, and something really special about it, it's got a single girdle that holds the whole thing together. So we don't have individual caps. We've got one girdle that we'd be pulling off. Really nice, a nice way to do it. That's the piston. Conrod. It's got a fairly skinny conrod. They do bend where this particular one doesn't look like it. This conrod, general rule of thumb, is somewhere around 650 newton meters of torque at the wheels is about the upper limit. As soon as you start going any more than that, she'll bend, then she'll put a window in the block. So keep that in mind. All the pistons are out, they're on the bench here. I did manage to find the bearing for cylinder 3, which it's absolutely destroyed, but all the rods look like they're in really good shape. We're not going to be using these rods or pistons in a rebuild anyway, so realistically they're all going in the bin, but it's nice to know that the thing was running pretty well, except for that bearing. We'll pull the crankshaft out now and see what sort of damage is there from that. So that's our girdle, nice cast thing, comes in one piece, so that does stop the whole bottom end from twisting under big power. It's a pretty special piece. Front plate here actually houses the oil pump. The balance shaft is behind here. This is that balance shaft belt I was talking about. That's the crank trigger again. That's the crank trigger pickup just here. That's where I'm up to. So keep in mind as well, the timing belt's already off. When you do a timing belt on this engine, you don't have to replace the balance shaft belt, but it is good practice. And the other problem with this is that in the car, remember that it's an east-west style engine. The wheel is normally somewhere along here. Pulling this bolt off, it's bloody hard work. Down to the crank bolt, one of my arch nemesis on this one. Not too hard to pull apart. No, I'm just kidding. That was really, really hard, so we pre-prepared for that. Crank bolt out. No. Well, she has fought me every step of the way here, so pulling the timing gear bolt out was hard work. Pulling the timing gear itself off, very hard work, but the Mitsubishi does do it pretty nice where they actually put an M12 bolt thread in there's 4 of them in the front of the timing gear, so you can put 4 bolts in, tighten them bit by bit by bit, and eventually take that real tight gear off the front of the crank. So that's a really nice thing to do. But now we'll pull that whole timing plate off the front, which is going to release our oil pump assembly. It's also going to release both our balance shafts and let us pull the crank out. So there's our crankshaft. They're a pretty tough thing in the standard 2-litre engine. When they break, I have seen them break before around the journal for cylinder 4 here. Incredibly, I've actually seen one of these crankshafts break and then the engine still run enough that it would catch and run, and you couldn't quite understand why, but it was because the crankshaft was broken. What's not so good about the 4G engine? The balance shafts. The thing has got 2 counter-rotating balance shafts that spin inside the block, one on either side. One of them, this one here, this is the oil pump assembly here in the timing cover case at the bottom. To be honest, I don't really understand why the Mitsubishi engines had the balance shafts the whole way through, like whether there's a fundamental balancing problem, whether Mitsubishi were trying to do something special and make it a super, super smooth running engine. I can't imagine that's the case because the twin balance shaft and the complexity of it doesn't really, in my opinion, make it any smoother than one of its competing engines without a balance shaft system. Now that the engine's stripped down to pretty much nothing, we flip her over a bit, you can see the oil squirters that I was talking about before that are spraying up the bore onto the bottom of the piston in order to take some of that temperature out of the piston crown and bring it back down into the oiling system, then out to the factory oil coolers that the late model Evos have had in order to basically just keep combustion temperature down, being able to make more power. Other than that, inside this thing, it's big, it's tough, it's heavy, it's a good block. Now, while Subaru didn't invent the boxer engine, many would say they perfected it. They've had a long and cherished motorsport history. The EJ has collected millions of fans worldwide. So let's dive in and see what's so special about the Subaru EJ platform. Okay, before we go any further, let's get the definitions of a flat and boxer engine right, because they're not interchangeable. A boxer engine is a flat engine with a pair of pistons connected to a different crank pin mirroring each other. But not all flat engines are boxers, because a flat engine can also have piston pairs sharing the same crank pin, working in the same fashion as any other V configuration engine. So while all boxer engines are actually flat engines, not all flat engines are boxers. Are we clear? Okay, so with this out of the way, we can move on to the hero of this video, Subaru's EJ series engine. The late EJ series is considered by many to be the pinnacle of the Japanese boxer technology. But Subaru's strange obsession with flat four engines started way back in the 1960s. They released in 1965 Subaru's first Boxer, which was a 900cc water-cooled engine known as the EJ52. It made just 55 horsepower, which was actually not too bad given that it was fitted to a car that weighed only 550 kilograms. Subaru continued to develop the Boxer engine, investing a considerable amount of resources into a platform that would eventually lead to the EJ. The EJ series made its debut in 1989 in the Subaru Liberty and the Subaru Legacy in the North American market. It remained in production until 2021, making it one of the longest running production engine platforms of the modern era, and it was the mainstay of Subaru's engine line. It was the EJ that gave Subaru international clout, powering its World Rally Championship cars. And of course, we can't talk about the EJ without mentioning the famous car it was fitted into, the mighty WRX. In 1992, Subaru partnered up with British engineering firm ProDrive to develop a new compact chassis. Based on the existing Impreza, it was dubbed WRX, which stands for World Rally Experimental. And it featured an all-new four-wheel drive system and a powerful turbocharged EJ20. The engine was rated at 250 horsepower at all four wheels, but rumour has it actually made closer to 300 horsepower. In the super capable hands of Colin McRae, the famous 555 WRX STI went on to win the WRC Constructors title for 3 consecutive years in 95, 96 and 1997. Due to their reputation as a compact, reliable engine platform, the EJ20 can be found in numerous amateur and professional motorsport series. They've also been a popular conversion for Volkswagen guys as a modern, flat-four successor to the ageing air-cooled engines. And, along the same lines, are a popular engine for kit cars based on the older Porsche models. The EJ engine has been produced in over 20 variants since 1989, which means two things. There is plenty of options to choose to suit your requirements, and depending on the model, they can be plentiful and they can still be affordable. You can split most EJ engines into two groups, pre-1998 and post-1998. Both groups include naturally aspirated and turbocharged variants. An easy way to tell if it's an earlier or later model EJ is by looking at the engine code. The earlier models end in a letter, like EJ20G, for example, while the later ones end in a number, like EJ205. For performance builds, the most desirable EJ would probably be the EJ207. These were found in STIs made in 1999 and then 2001 to 2005. They come with a forged rotating assembly that tends to enjoy higher boost levels than the other variants. Of course, it is possible to turbocharge a naturally aspirated EJ or increase the boost on turbocharged ones. But keep in mind that the factory cast OE pistons found in most EJs are considered a weak link, would normally need to be upgraded. When it comes to modding an EJ series engine, thanks in part to the standard architecture, it's common to mix and match blocks, cylinder heads and rotating assemblies depending on your build and what's available at the time. There are plenty of setups making 300 to 350 horsepower on a stock engine with basic bolt-on mods. But if your horsepower aspirations are in the 400 plus region, you'll need to look at an even bigger turbo, an upgraded intercooler, upgraded fuel system, and serious engine internals, including rods and pistons. While you're there, a set of head studs and a quality head gasket just makes sense. Just like any engine, there are some caveats. Subaru factory turbocharged engines do have a reputation for burning oil, sticking ringlands, and if abused or mistreated, cracking pistons or worse. Remember that the WRX and the STI models were sold as performance vehicles, and it's safe to assume that every one of them has had a pretty hard life. Even the non-turbo engines will still need a good check over, as the cramped engine bay of a double overhead cam Boxer engine or a quad cam makes them difficult and expensive to maintain. Doing a set of spark plugs on some of these models is an ordeal and often skipped over until there is a problem. Now, I mentioned earlier that the factory pistons and connecting rods are considered a weak point and are commonly upgraded in performance builds. But due to the age of these engines,
If it's coming apart for any reason, it's worth looking at a set of rods and pistons to ensure reliable operation moving forward. There are some who believe the factory oiling system isn't adequate, but consult your engine builder before pulling the trigger on a high volume oil pump, as there are a lot of differing opinions here. Personally, I'm pretty neutral either way. And of course, there is the head gasket issue. Now, to be clear, there has never been an official head gasket recall by Subaru. And Subaru are actually pretty good with their voluntary recalls. But there's enough solid data out there to say the factory head gaskets are prone to failure at 150 to 200,000 kilometres. And once again, because of its flat 4 layout, replacing head gaskets on an EJ is an expensive job. But geez, they've provided us with a lot of memes, haven't they? It's not all bad news. First, there is some good news. Not all EJs are heavily affected. It seems that the models most prone to head gasket failure are the EJ25s, like the one that we've got right here, produced between about 1996 and 2004. Interestingly, the problem seems to be more prevalent in the naturally aspirated and the single overhead cam variants. So, should that stop you from getting an EJ? Well, look at it this way. If you're planning to put that engine in your race car, then you're probably going to do all the upgrades to the internals, and changing head gaskets will be part of the job anyway. Knowing the common issues and the limitations of what engine work's possible without removing the engine will help in planning your build. Aside from the common problems, and let's face it, every engine has some, the EJ is a snappy and great sounding engine, well, in my opinion, with a low centre of gravity. It's a relatively reliable engine to use as an upgrade in your existing Subaru, an engine swap into a VW or a kit car, or as a fully built monster for your dedicated race car. So without further ado, these things are pretty interesting to pull apart, so let's get out the spanners and see how it all works. Now, if you haven't had the fortune of opening the hood of a WRX to see what the engine looks like, this is it, and it is a little bit unusual from your normal inline 4-cylinder or your V8 style setup. This thing's got a cylinder head on this side, a cylinder head on this side, the intake manifold over the top, the exhaust manifold is normally underneath, and the crankshaft goes down the middle here. Here's the harmonic balancer, and the block or the casing is here and here. So I'll get to it, we'll start stripping it down, and we'll get to the part where we've got just the block sitting there. This is very different to the other teardowns that we've done because there's a little bit of a complicated way of getting the rods and pistons out of this thing. So there we go, there's our intake manifold or our intake plenum. It's got an electronic throttle body hanging off the side of it there. Electronic throttles in these cars were typically introduced around 2006-ish, pre-2006, cable, after electronic throttle. There are some exceptions to that, but that's a pretty reasonable thing to think. What I did want to show you here is these things, the tumble generator valve. So what happens here is that we've got a stepper position, a stepper motor with a position sensor. We've got 2 of them, one on either side. These things are the source of some diagnostic trouble codes and engine lights in some of the Subaru families where they'll get stuck or they'll have position sensor problems. Basically what's going on here, a tumble generator valve. So this thing is used and we map that open or closed or a particular position depending on the engine RPM, basically to increase airspeed for the engine, so to increase drivability. One of the mods that a lot of people do on these is to remove the tumble generator valve. The STI variant actually does not have this in there at all, so you could replace that, or you can pull that shaft out altogether. There have been times known where the screws that hold them together do fall into the engine and cause problems, but pretty rare. There's our fuel injectors there. They're spraying in through the top of the tumble generator valve. Then they come down through the inlets on the cylinder head, and that's where our charge goes straight in. Next up in the Subaru adventure are these 2 things. Now these help with Subaru's secondary air pump system. What's happening there is to pass any of the emission standards that this thing needs to pass. These are here to pump air into the exhaust system while the engine's cold. Basically, they're helping the catalytic converter in the exhaust to get up to temperature as quick as possible. Then, once they're up to temperature, the catalytic converters take over, and the air pump's typically not used after that. Again, these are another thing in the Subarus that do cause a lot of check engine lights. The air pumps often fail, so that's one thing to have a look for. So this thing here is the water neck, and that distributes water from the radiator either side to the engine here and uses O-rings to seal that on the block. So there's the factory knock sensor. So 2-wire sensor, and that's the factory position for the knock sensor right there. So there's our crankshaft position sensor out. That's a 2-wire reluctor style sensor. Because it's a Subaru, the camshaft position sensors, I'll pop that one out and I'll pop that one out. I've got a seal there so they don't leak. Are 3-wire Hall effect sensors for the camshaft. A little bit unusual to have a reluctor style crankshaft, Hall effect style camshafts. That's pretty typical of about an 01 onwards model. 2000 models and down had reluctor crank sensors and reluctor cam sensors. So that's a single wire oil pressure switch. That's basically telling us, do you have oil pressure or not? It doesn't actually give us a value. If we need to see a value for the oil pressure, we would typically replace this with a 3-wire full pressure sensor that'll give us the working range of say 0 to 150 PSI. I'll just pop these cam control solenoids out. Interestingly, they look pretty similar to most other engines, the way that they do that oil control. So basically what we're doing with these things is oil pressure is fed into the solenoid, then we either choose to allow it into the cam gear to advance the camshaft, or to sit at a duty cycle that's our hold position to hold the cam in gear, or reduce that duty cycle in order to let the pressure out of the cam gear, in turn retarding the camshaft. Pretty similar principle, pretty similar looking thing across most families of engine. Next up, the timing cover case, and we'll see what's going on inside there. So next time you need to do a timing belt on your 4G63 or your RB or your 2J, or hell, if you need to do a timing chain on your SR20, spare a thought for the Subaru guys. Welcome. This is what's going on. We've got a cylinder head over here, a continuously variable camshaft up here, the fixed exhaust cam down here, the belt, we've got an idler, the crankshaft, we've got the crankshaft position, the tone wheel behind here, that's where the position sensor came out of, just here. We've then got the tensioner. We've got another continuously variable camshaft here. We've got a fixed exhaust camshaft here. The belt comes here around the water pump, which I'm shocked that in the state that this engine is in, it's actually had a water pump on it. Then back, just throw in another idler, and then we're back to the other side. Oil filter that's got a cooled base. That is a hell of a timing belt and definitely not something for a first timer. This is complicated to do on the engine stand right here. Can you imagine doing this in the front of your car when the radiator and your air conditioner that you don't want to evacuate is sitting about here? In case you're still interested in doing a timing belt on one of these things, the timing marks can be found here, 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 and here. They're really well marked, so that's one of the really nice things. So this thing is sitting on top dead center right now. So next I'm going to take the timing belt off. I'm going to do that by removing the tensioner. I did have the motor on top dead center to show you those marks, and I've just wound it over so that all the pistons are sort of not at TDC, so that when we take the belt off, there's no chance of any valve hitting any piston. I think that's really good practice. Even if you know it's a non-interference engine, still good practice because you never know, and the one time that you don't do it, you are going to get in trouble. So now that we've got the whole front of the engine stripped, I'm going to flip it. Here we go. And this is a lot more of a familiar sight because we've got a cylinder head up the top There we go. 1 ignition coil out, 2 ignition coils out. That's a 3-pin coil. It's got a built-in ignition module, quite a powerful ignition system for this style of engine, so they do pretty well. There we go. That's 1 rocker cover from one side. Sealed with a gasket, bit of blue on there as well, so somebody's been in there tinkering. It's got a bit of silicone everywhere. Probably find that down in the oil filter and the oil pump. So as we take the caps off, pop them to the side, we can see here that we've got our normal camshafts, we've got our intake lobes up the top here for 2 cylinders, we've got our exhaust lobes down here for 2 cylinders, then we've got 2, 4, 6 bolts that are holding on the intake, 2, 4, 6 that are holding the exhaust, we've got the oil supply for the intake for the VVTi. Interestingly, on the exhaust side here, there's also the grooves there for the oil supply, because this engine did come with dual AVCS or dual variable cam control. The holes for the spark plugs, very, very nice. I don't know why the pattern looks like that, but I think that's pretty cool. I like the look of it. And there you have it. 6 head studs from one side of the engine. These things are super long. Whether that plays a role in head gasket dramas in these things, I don't know. As far as torsioning these things up, obviously the longer that the stud is, the more problems we're going to have getting equal torsion when we're tightening this thing back down. Just for interest stakes, I was just curious to measure this thing, and from the mating surface of the bolt across, 170 millimeters or 6 3/4 of an inch. So it's a pretty serious head stud, or head bolt, I should say. And there you have it. The Subaru cylinder head, that's 2 cylinders. We've got 4 valves per cylinder, 2 intake, 2 exhaust. This, obviously where the spark plug is. On this side, the block, here's the head gasket, the Subaru head gasket that everyone talks about. Doesn't look too bad at the moment, but watch this. When I pull the head gasket off, this is the bit that always surprises me. Got a couple of dowels. So that is the head gasket for one side of your engine. Pop that in there. This is the bit, the open deck. So what's going on here? There's not a whole lot that's supporting the bore of this engine. So there is semi-closed deck and closed deck versions as well. Basically what that means is how much around here is filled with metal or with material, or how much is open with coolant running there. Coolant, excellent for cooling the engine, really good for a very low horsepower factory style car. The more power that you're making, everything starts to wander around, and that's where we start to have problems. There we go, we've got the other side out. We're about to pull the head studs out, but before that, a couple of things to point out on the camshaft. Hollow camshaft and the cam teeth. So this has got the cam position sensor that comes through the back here. We'll have a look at this camshaft. It's got 3 teeth spaced 90 degrees apart. So basically it looks like it could have had 1, 2, 3, 4, and there's 1 tooth missing. That's our unique position. So we get an idea of where top dead center 1 compression is. Can you believe that? Pulled a cylinder head off both sides of this Subaru, and the head gasket, admittedly a lot of other things on this engine look a little bit nasty. No blown head gaskets here, both of them look all right. Now here's where things get a little bit interesting with the Subaru. So I've gone through and I've loosened off as much as I possibly can, but we've got some plates inside where the bell housing is now. I want to take it off the stand and put it on the bench. I'm going to take those 2 plates off because then we've got 1, 2, 3, 4 plugs that we need to pull off. Then we're going to get in through those. We're going to get the retaining clips off the gudgeon pins. Then we're going to hit the pins out. Then that's going to help us pull the whole thing apart. Well, it's the only way to do it. These are the plates I was talking about, so we'll get rid of them first. Now with these 2 inspection plates off, you can see what I was talking about. So 1 inspection plate off. If I grab my torch and if we get a close up in here, that looks familiar in there. There's a retaining clip and a gudgeon pin. We get our inspection, hopefully we've lined her up. There she is, there's the other gudgeon pin and there's a retaining clip there. So I'm gonna get my long nose pliers and I'm just gonna try and knock both of those out. The next job, as agricultural as it sounds, is we're going to get an extension bar and we're going to belt through and we're going to try and knock the pin out of the other side where the retaining clip's no longer there. So we'll spin the engine around again until we get to a position where we can see that. Then we'll knock her out. This bit's crazy and it looks dodgy, but this is how it is. There's your wrist pin or your gudgeon pin. Just came out of the bell housing side and the engine's not apart yet. So that piston is no longer attached to that conrod. 1 down, 3 to go. It's a boy. And here we go. It's taken a little bit to get there, but we now split the case. So essentially, the block is going to split in 2, which is also our main bearing holder assembly. So when we slip this part apart, we're going to see the crankshaft, and we're going to see the rods hanging onto the crankshaft, but the pistons are just going to kind of come out of the sleeves because they've got no gudgeon pins on them. It's worth noting that once you've taken all the bolts out of the covers, there is a sneaky one in here, and there is a sneaky one in the front as well. That's our timing gear, so we spoke about that on the camshaft. This is the trigger teeth on the crankshaft. Very important to make sure you don't nick one of these teeth or scratch it, because if you do, odds are you'll have trigger problems down the track. So that's our oil pump assembly. That's our front main seal, the oil seal. The drive type on this thing, it's just got 2 flats on the front. Very similar to the Nissan GTR style pump drive, interestingly, so it's not a multi-star style setup. Just 2 flats that it runs against on the crankshaft, and that's it. Have a look here. Whew. There's your rear main seal, so that's the one behind your automatic transmission or your clutch or whatever your car may be. Here we go. Whew. And there you have it, EJ. Looks easy, right? So now that we've split the block, I can gently get my hammer in here and I can here comes the crankshaft. Wiggle him out. And our connecting rods. I'll just pop that the front there. Then we've got the other half of the block. And there you have it. That's the absolute basics of your EJ engine, how the block splits, the pistons look like, what the gudgeon pins look like. What's interesting, it is quite heavy, but look how cute the crankshaft is. She's tiny, but you know that because when you look at the engine, essentially it's two-cylinder engines that are 180 degrees opposed. Amazing. Certainly an engineering masterpiece, and they do sound amazing. Well, I've definitely been looking forward to this episode because I do love an EJ teardown. A lot of people that haven't had a huge amount of experience with Subarus, I'm sure will be surprised with the way that these things come apart, with what the crankshaft looks like, with how those pistons are pulling in and out like this. It truly is an amazing thing. Look, they are difficult to pull apart. They are even more hard to put back together, and credit to the guys that are building these things and that are making huge horsepower out of them. There are EJs in excess of 1,000 horsepower, and that be absolute credit to the engine and to those engine builders.
I'm going to go out on a limb here and say that the 1990s were the golden age for performance Japanese engines. We've got the 2JZ, the RB, the 4G63 and the Honda K series, all over-engineered, all capable of producing power well above their factory spec. But there's also another engine that we haven't covered yet, and this one definitely belongs in that group. Nissan's SR20.
Couple Nissan SR20 motors will pull up premium 1 week before race wars, huh?
The SR series engines were designed as a replacement for the aging CA series and came in a variety of models and capacities. But today, we'll focus on the SR20 DET, which is the performance model of the group and the successor of the mighty CA18 DET. What exactly is the SR20 DET? Well, like all Nissan engines, it's right there in the name. SR is the engine series, 20 refers to the engine size or the capacity of 2 litres, D stands for dual overhead camshaft, E stands for electronic fuel injection, and everyone's favourite, the T, of course, stands for turbo. Here's a fun fact. Most car enthusiasts will tell you that the SR20 DET is a longitudinally mounted engine, that is north-south orientated. However, the turbo engine was actually introduced first in a transverse engine configuration in the engine bay of the Nissan Bluebird 2000 SSS. Even more transverse engine placements followed in the 1990s when the SR20 appeared in the engine bay of the Pulsar GT-IR. It wasn't until 1991 that the SR20 arrived in the longitudinal placement that we all know and love, in the Nissan Silvia S13. A nice, lightweight, rear-wheel drive car that was perfect for drifting. The SR20 Turbo stayed with Nissan's S chassis until it met its end in 2002. Horsepower junkies will often argue against the SR20 DET engine since it's not based on an iron block, or that its output can't compete with that of an inline 6-cylinder like the RB and the 2JZ engine. However, obviously a 4-cylinder compared to a 6-cylinder, things are never going to be exactly the same. However, there are compelling reasons to go down the SR route depending on your application. The SR block is aluminium, which in front engine rear drive setups helps to maintain the excellent weight balance that the S chassis is known for, and in turn contributes to desirable neutral handling. The RB and JZ engines do weigh quite a bit more, which puts more ballast towards the front. That's fine for a drag car, but if you're wanting to go around corners in a drift, a rally or circuit style, it's less than ideal. So which SR20 to get? As I mentioned, the versatile SR20 was produced for over 13 years in practically every configuration imaginable, from naturally aspirated to forced induction to all 3 driveline options, front-wheel drive, rear-wheel drive and all-wheel drive. Early S13 SR20s were commonly identified by their valve cover, the red top and the black top. These were sometimes referred to as flat top as well. Engines came with a high port cylinder head with non-variable valve timing camshafts. These engines made use of little 370cc fuel injectors and a Garrett T25G turbocharger taking care of the forced induction side. All this translated to 205 stock horsepower and about 200 pound-feet of torque. S14 Silvias came with Nissan's newly updated SR20 DET with variable timing control, or VTC. This engine, characterised by its unusually shaped valve cover, earned it the nickname notch top and slant top. The new cylinder head, known as the low port, features a redesigned intake manifold feeding slightly smaller ports for increased intake velocity. This engine received a larger Garrett T28 turbocharger, which combined with the VTC and the new cylinder head design offered improved response while delivering greater peak power of around 220 horsepower. In 1999, Nissan unveiled the final S chassis to be powered by the mighty SR20 DET engine, the S15 Silvia. The SR20 that powered the S15 Spec R continued to benefit from the VTC cylinder head and came equipped with a Garrett GT28R ball bearing turbocharger, bigger injectors at about 480cc, and the new coil-on plug style. So this eliminated the dumb coils with the external igniter in favour of the smart coils that had the built-in ignition module. An improved engine management system regulated the fuel delivery and ignition timing to produce nearly 250 horsepower. So which one of these is the best? Well, they're all fairly solid options, and all of them can make pretty decent power, but my pick would be the version found in the S15 Silvia. Or, if you can find one, the S15 Silvia that somehow has a Neo VVL head with the variable timing and lift control, but this was never found in the Silvia platform. Just like any second-hand engine, there's things that you'll need to look out for when you're buying. This is especially so when that engine originally came in a Japanese performance car and has more than likely had a pretty hard life and has got a pretty bad service history. SRs can suffer from oiling issues. The oil pan is relatively small and the oil pickup is located only a few millimeters from the bottom of the pan. So if the pan takes a hit, then it can in turn hit the pickup, which will crack at the top and you'll lose suction. In that turn, the engine's not going to get the oil it needs to survive. With that in mind, it's the high wear areas that you'll want to pay close attention to due to the age of these engines now. Hard driving conditions and age are certainly wearing rings and cylinder bores, while low oil pressure can lead to spun bearings. And as many of us know, SRs commonly throw rocker arms as a side effect of valve float, so that's something that you're going to know about pretty quickly. Like any engine that's starting to get a bit long in the tooth, it also wouldn't hurt to take a look around the injectors and ignition system if you're planning on using any of the original stuff. SRs are well known for throwing rocker arms, so if you're taking the valve cover off to upgrade the camshafts, it's a good idea to add a rocker arm stopper kit to keep them in place. If you're super hardcore, you'll ditch the hydraulic valve lifters in favour of solid lifters. And since solid lifters can't really pump up, they reduce the chances of rocker arms being flung from their positions. When you're ready to step up to the next level, it's time for engine internals. The alloy cylinder liners of the SR20 can only be overbored 0.5 mil or 1/20 of an inch twice before the liner walls are too thin and you're forced to re-sleeve the block. There's no shortage of aftermarket internal engine parts for the SR20, including stroker kits or even billet cranks like this work of art from K1 Technologies. As always, improving the airflow in and out of the cylinders is going to improve performance. You can install higher lift and longer duration camshafts along with larger valves and portwork. But remember, bigger isn't always better. Going big with high peak power output is great if you're drag racing, but usually means down-low torque will suffer. So make sure you're getting the right cylinder head work for the kind of work the engine's going to be doing. One of the most popular modifications to the SR20 is to do the VVL Neo or the VE cylinder head. Now, this head never came in a stock S chassis. It was, in fact, in the JDM spec Primeras, Bluebirds, and believe it or not, the Nissan X-Trail, which is rarely seen as a performance vehicle and more of a soccer mum kind of machine. The VVL heads got improved airflow in the factory engine, had higher compression, and improved coolant passages, and in my opinion is the best base to start with in a performance SR20 package. But keep in mind, an SR20 VVL cylinder head only is going to cost you about as much as a whole S15 SR20. If you're thinking about taking your SR20 apart and upgrading the internals, I highly recommend doing an interactive engine building course with High Performance Academy. They actually have one specifically for the SR20, so we'll put a link to that course in the description from this video. Okay, it's time to get down and dirty, and this is the part that I love the most because I get to pull these engines down and I don't have to put them back together. Just a quick note before we start, the engine we're actually using here is a naturally aspirated SR20 DE that we sourced from a Nissan Pulsar N15. This is the non-turbo front-wheel drive engine, so let's strip it down and see what's inside. Okay, rocker cover off. First thing we can see, the thing does have two camshafts. Got the inlet cam, got the exhaust camshaft. It's got a row of oil squirter along the top here that sprays oil down onto the cam lobes. It's a timing chain style engine, not a timing belt. On this side, one of the nice things to see on the SR20 is the way that the intake works here. Typically, we've got a flat inlet manifold mating surface, whereas this one is actually tilted up. It's got a huge long intake runner and the inlet manifold isn't even bolted on yet. If we look down here, we've got a pretty clear shot straight to the inlet valves, quite a nice thing. I think what we need to do now is strip the outside of the engine before we can pull all the timing cover case off and have a look what's on the front. One of the things that's fundamentally different between the north-south and the east-west engine, or the front-wheel drive, all-wheel drive, or the rear-wheel drive, is the water system, so the coolant system and where it comes from. So this thing's got a huge bunch of intake piping and stuff that goes from the thermostat, where the thermostat's mounted on the back of this engine, and a whole bunch of water pipe. Because remember, if it's round the other way, all the coolant and where the radiator is, everything's completely different. Up under the inlet manifold here, we've got our knock sensor. We've got an oil pressure switch. This comes in handy on the SR20, and I'd recommend, if you are doing a rebuild, remove the oil pressure switch and change it to a sensor. So that switch simply turns on and off about 3 psi. So if you've got below 3 psi of oil pressure, the light comes on, you know you're in trouble. You can replace this oil pressure switch with an oil pressure sensor, so that instead of just seeing whether you're above or below 3 psi, which is what the switch does, you can change it to a sensor so you can measure the actual oil pressure, and you can do your engine protection against that oil pressure. Being a Nissan block, this is going to be a 1/8 BSP thread, so make sure to get the right adapter when you're buying your oil pressure sensor. Okay, here we've got the ratcheting timing chain tensioner. So once you pull it out, it's got an O-ring in there as well. Basically what's happening here, if I just try and push against this, how it works is we squeeze it up against a spring that's in there. It's normally got a little latch here that hooks over so that it's kind of armed. Think of it like a grenade, that sort of style thing. So it's locked and sitting there waiting. We would assemble the engine, we'd put it in. As soon as you flick that lock over, it'll spring out and it would then tension the chain to the right spec. There we go, and that's the water pump. Gets driven by one of the drive belts. Considering how nasty that cylinder head is in this thing, it's got pretty nice green coolant in it. See, and that's how easy it is to get any balancer off just about any engine. No, I'm just kidding. Every time we do an engine teardown, getting the balancer off is the part that I worry about the most. Because whether you've got the right tools, whether you've got pullers, whether you've soaked the thing in some type of an invasive sort of lubricant, they are so difficult to get off a lot of the time. Luckily with this one, she came off pretty easy. While we're here, this here is the timing pointer on this engine. So a little bit different, so it's not on a timing cover case and it's not sort of molded into any plastic. So when the balancer's here, we've got the pointer and then we've got the timing marks here on the balancer. So that's what you're looking for when you're using your timing light. You might notice here the timing cover case. So we've got the cylinder head just here. Then we've got the timing cover case, this bit just here. This is the crankshaft with the front seal. So pretty rare. Sometimes you could have a front seal leak where oil's coming out the front. That'd be that seal there. You can see why it's so time consuming to get to that now that the engine's stripped down. It's quite a lot of work to get here. There's a seal along the bottom here. That's the sump. And everything's all glued together. There's a problem here, and what that is, compared to a car with a timing belt, with the timing chain assembly, if you're getting any cylinder head work done, once we pull this timing cover case off, you're going to notice that the level here, this is one cylinder head from here to here, but we've got block from here to here, then the timing cover case on the front. So make sure if you're getting any engine work done, you need to supply the timing cover case. Don't send this part away to get painted or do something else or forget to send it, because if you deck the head just that little bit or you deck the block just a tiny bit, you'll assemble everything and then everything will foul on the timing cover case. So whatever you take off the block, you also need to take off the timing cover case. So if you like SR20s, you would have heard somebody talk about throwing a rocker arm. So let's have a look and show you what that actually means in here and why that's so painful. So the first thing we'll do here, we'll just pull the arm. So typically where the camshaft was sitting, the camshaft was running on these smooth surfaces along the top here. The camshaft, as the lobe's going, it's pushing up and down like this. So let me pull this arm off ever so gently. Okay, so this is the rocker arm. It's got the pivot point off the lifter at the back here. Then it's got the 2 points up here that run on each of the valves. One shim, there's 2 shims. So what's going to happen if we bounce the thing off the rev limiter? It's probably one of the big tuning tips for this thing is that if you're doing an ignition style rev limiter, it'll make that really loud banging when you're on the rev limiter or when you're on the 2-step. The problem with that is it unsettles all the valve train in the SR20, and you'll find that these 2 little friends here will end up in the sump somewhere. So 1 or 2 of them will end up in the sump. So what I'm going to do is put them aside, then I'm going to put the rocker arm back on. This one, nice and solid, everything's there, everything's shimmed perfectly. This one, it's moving all over the place. This is the problem. Those little shims will end up in the sump somewhere. Hopefully, if you pull over in time, you could pull the cover off. You might be able to find it sitting in the cylinder head somewhere. That's where it's all gone wrong. So the idea of using a fuel cut for the rev limiter rather than ignition cut is certainly going to help. And if you've got an SR20, I know all the drift guys do it, but please be reasonable on the rev limiter. Don't hold the thing flat out on the rev limiter the entire time. The longer you're on the limiter, the more chance that one of those shims is going to fly out, and then you've thrown a rocker arm and you're in trouble. If there was an Achilles heel of the SR20 engine, I'm going to say that this is it. It's either the alloy block or it's this rocker arm setup where the CA18 before it, the RB26 that ran parallel or slightly after it, didn't have an issue like that. It didn't have rocker arms because we had a camshaft that went straight down on top of the bucket. That bucket ran straight on the valve and the valve spring. So we didn't have this sort of rocker arm setup. If you're going to complain about something on your SR20, this is probably the area that you're going to be complaining about. I don't like the rocker arm assembly on this setup because of how much trouble it makes. The best thing you can do to avoid problems like this is get a high quality camshaft and or fit what they call like a rocker stopper arm kit. So think about it. So as those valve springs are going up and down and riding on that camshaft, if we've got uncontrolled cylinder pressure, so whether we've got detonation, whether it's on the 2-step, whether it's smashing off the rev limiter, think about what those valves are doing. They're opening and closing, riding on the camshaft, but for a split second, if they come off that camshaft because there was something that happened in that cylinder that made that valve bounce up and down, or you get valve bounce, or you're revving the thing too hard, or whatever the case, these little arms, there's nothing there to hold everything together. So that rocker stopper kit, think of it like a bunch of fingers that are holding down, so they're always just putting a little bit of preload on everything so that if anything does become uncontrolled, as a last line of defense, we've got that rocker arm stopper kit. Now these little hydraulic adjusters sit on either side of the cylinder head, then rocker arm sits within that, then rides on the top of the valve spring. So keep in mind, if you've got really bad oil pressure, your lash adjusters aren't going to be getting the oil pressure they need, and then they will also become slightly looser, slightly lazier. They'll drop a little bit of compression, and then before you know it, it's another reason why we're going to have rocker arm problems. So if you keep on throwing rocker arms and you just simply can't see a problem, maybe have a look at your engine oil pressure. This is one of the messier parts with SR20, is that you actually have to remove the upper and lower sump in order to pull the timing cover case off, in order to pull the cylinder head off. So if you're going to be doing a cylinder head gasket or something like that, probably not a reasonable job to be doing in the car. The engine really needs to come out. So this one's not a great example of an SR20. The bottom, it is super
gummy and gloopy down here. But I just wanted to show you, so this is the baffle that we've just taken out. There's a bunch of 10 mils that hold that in. Pull that baffle out and you can see this is the oil pickup I was talking about. And then this is the lower sump, so we'll remove that as well now. The timing cover case that we've just pulled off so we can pull the cylinder head off. This is the oil pump in here. We normally don't pull these apart. You'd either replace it or you'd know that it's good. But while we're here and we're oily, let's pull it apart and we'll see what's inside. On this style of engine, the oil pump has got two flat surfaces, just like the RB style engine. Got one bolt, we'll just slide this off. We've got in here, there'll be a pressure relief spring along there that sets your max oil pressure. This is coming from the pickup in the sump. So before, that would have been mounted that way, sitting something like that. Here's a tip, whenever you're replacing this, make sure you do put the gasket in there. One of the really common things is not sealing here and always having a low oil pressure problem. Our pump gears are turning like this. And what you'll notice is that here, as the thing's turning around, the crankshaft is spinning in here, and that's always spinning perfectly on its axis. Then oil's coming in through the feed here. And then as this thing spins around, the gap gets tighter and tighter and tighter until it compresses that oil within the gear and then spits it out the feed into the engine. Okay, we're pretty deep into this motor now, where we've got pretty much everything out. The block and the crankshaft are still there, but we'll get to that. This here is the factory piston, the cast style piston. It's got two rings up the top, so it's got the compression rings up the top, and then down the bottom here, the two thin rings and the little wobbly one, so that's the oil control ring. It's got our gudgeon pin in the middle here, so there's a pin that goes straight through the middle here to hold the piston to the conrod so that it can wobble as it goes up and down. We've got our conrod, we've got our rod bolts, and then we've got our big end bearings that go in here. So a couple of things on the SR20. The conrods don't look super impressive, but they're not terrible. They will make sort of 250 kilowatts all day. If you start going further than that, you'll typically find it's a rod bolt is where things are going to go wrong. So it's going to break a rod bolt and then it'll rapidly disassemble. Below here, we've got our big end bearings. So these are the bearings that sit in between the conrod and the crankshaft. Pulling this motor down, I don't know whether we can get a close up of this, but these bearings are absolutely toast. So judging from the look of the top of this, all of the cylinder head, how much goop is there, how much hard work this thing's done with very few oil changes, I'm guessing. Now more than ever, it makes sense to strip the engine down and put some rods and pistons in it before anything goes wrong. Back in the day, you could get a long engine, a wrecker engine, throw it in a car, tune her up. If it did break a piston or break a conrod and it took the block out, it wasn't such a big deal. Now, it's super good investment to put rods and pistons in the engine before it fails, because you never know if you're going to be able to get a new engine. You never know if you're going to be able to source a spare block if any damage occurs. This here is a forged piston compared to the factory Nissan style piston. Admittedly, this one's brand new. This one's probably done 200,000 or 300,000 kilometers. So this one does certainly look nice and shine out. Truthfully, it's a shame to put this in the engine and hide it away where you can't see it. So now the crankshaft is out of the SR20. This factory crankshaft is actually quite good, and they have been known to support huge horsepower in some of the Pro Mod style SR20s. However, they aren't super reliable at the massive horsepower levels. So
If you are sort of looking at the 1,000 horsepower and beyond range, you'd be looking at an aftermarket crankshaft, something like this one from K1 Technology. If you're a big fan of the SR20, but you're not too keen on doing this, rebuilding an old engine, I might have some really good news for you. Rumour has it, after over 2 years of negotiation, Nissan sold the tooling and the design files for the SR20 to a Japanese firm called Mercury Enterprises. The company plans to build crate engines and make them available to the public, but the initial quantities will be very small. We're talking maximum of 4 per month, so the wait for a brand new SR20 might be a few years. If you've just bought a Nissan Silvia, wouldn't hurt to put an order in, and in 5 years' time when you need a new engine, they might just supply you one. Well, we've come to the end of another engine teardown. This one has been fantastic, being a Nissan engine. There's been very, very few tools used. This thing has been an absolute pleasure to pull apart. Admittedly, it's not a really good example of the SR20 engine because it all belongs in the bin, but it has been fantastic to work on. I can understand why tuners and workshop alike love the SR20. As always, thanks so much for sticking to the end. My name's Scott,
And I'll catch you next time.